Welcome back to the Learning Studio. You're watching our mathematics series, where we uncover the hidden tools that power science, technology, and artificial intelligence. If this is your first time here, don't forget to follow us by clicking the link below. And remember, the full playlist is also in the description, so you can explore every episode in order. Today, we're exploring one of the most beautiful and practical areas of mathematics: Fourier Analysis and Wavelets. These tools allow us to break signals apart, study them in terms of frequencies, and put them back together in ways that fuel image processing, audio compression, and even deep learning. Let's start with a question. How do you describe a song? Sure, you could look at the sound wave, the up and down vibrations in time, but what if you want to know the notes, the frequencies that make the song? In the early 1800s, Joseph Fourier had a radical idea. Any signal, no matter how complex, could be expressed as a sum of simple sine and cosine waves. This breakthrough gave birth to Fourier analysis, a universal language of frequencies. And later, mathematicians extended this idea into wavelets, tools that capture not just frequencies, but also how those frequencies change over time. Here are the essentials. Fourier analysis. It transforms a signal from the time domain into the frequency domain. A sound wave becomes a spectrum of pitches. An image becomes a pattern of frequencies. Fourier transform. This is the mathematical tool that performs the translation. It's what turns your MP3 into compressed audio, your JPEG into a compact image, and your Wi-Fi into a working signal. Wavelets. Fourier analysis is powerful, but it struggles when signals change over time. Enter wavelets. Short, localized functions that can zoom in on both time and frequency. Think of them as magnifying glasses for signals. Applications. Wavelets are behind JPEG 2000 image compression, medical imaging like MRI, and denoising algorithms that clean up signals. Why it matters in AI and technology. Fourier analysis and wavelets aren't just theory, they're everywhere in technology. In image processing, they power compression, filtering, and edge detection. In audio processing, they help compress music, detect speech, and remove noise. In machine learning, Fourier and wavelet features help models recognize patterns in complex data. In communications, every time you send data over the internet or use your phone, Fourier transforms are working in the background. They're the mathematical microscopes of our digital age, letting us see signals in new dimensions. So, Fourier analysis and wavelets give us the power to decompose the world into its building blocks of frequency and time. They're the mathematics behind clarity, compression, and comprehension in a noisy world. In our next episode, we'll step into dynamical systems and chaos theory. Here, we'll explore how mathematics models complex nonlinear systems, from weather patterns and robotics to the delicate balance of chaotic systems that seem unpredictable but follow hidden rules. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each episode brings us closer to seeing how mathematics reveals the structure of everything around us.